I assigned to your groups a set of 4 problems, each of which is getting you to think about how to break apart one of these complex monomial arithmetic expressions and use the properties of exponents to simplify it, so that each power of a given variable is only written once. So problem number 4 starts with this product of minus x to the third power times z to the fourth raised to the second times 2x squared y to the third times z. So it looks like the first thing that was done here is that this exponent of 2 was distributed across the 3 factors inside the parentheses. And one of the easiest places to screw something up on a problem like this is to forget that this minus out here in the front is actually a secret coefficient of -1. And if you forget that, then you'll often forget to distribute that power 2 to it. But this group navigated it great. So -1 to the power 2, though I would recommend, just for the sake of absolute clarity, putting parentheses around that -1. -1 parentheses to the power 2, because as we know, there is a difference. This is what we wanted. But then, why is this x to the 6th? Where did that 6 come from? Yeah, x to the third raised to the second. That's a power of a power, and according to the power of a power rule, we multiply exponents when we raise powers to powers. So that explains x to the 6th. That explains z to the 8th. Then this group put both of those on top of a fraction with a denominator of 1 in preparation of perhaps needing to do some negative exponent work down the line. But it turned out that after they used the commutative property of multiplication to get the constants together, get the powers of x together, get the power of y, well there was only one of them, and get the powers of z together, there was no division happening, and so they just sort of walked away from that denominator, which is fine. We don't really need it here. But now that the powers of like variables are all together, we can simplify. -1 squared is 1 times 2 gives me a 2. The powers of x, x to the 6th times x to the 2, why is that x to the 8th? What are we doing here? We added the exponents, because when powers of the same base get multiplied, we can add their exponents. So x to the 6th times x to the 2 is x to the 6th plus 2, x to the 8th. The y's, well, there was only one factor of them in the first place, so we didn't have to do anything with them. And then the z's, where did this 1 come from, by the way? Yeah, this z, which is just by itself up here, the implicit exponent on that z is an exponent of 1. So make sure that you write it like this group did, so that you remember when it comes time to combine these 2 powers of z together that you need to add an 8 plus a 1 to get a 9. And so that gives us the final answer for this problem. So moving forward to problem 5, a little bit less going on here, but it introduces division, which is a valuable thing. So this problem asks us to divide y to the 4th times x to the 6th on the numerator with y to the 7th times x in the denominator. And it's already set up in such a way that we can use the division of powers principle that says that when we divide powers, what do we do with their exponents? Subtract. And the only thing to take a special care of then, whenever you're subtracting, is signs. Always keep the signs straight. And so what this group did is they said, well, let's look at the y's. We've got 4 of them upstairs, 7 of them downstairs. So when I subtract, I'll subtract 4 minus 7. And that's going to give me -3. And so at the end of this division, what I end up with is -3 powers of y to the -3. And then for the x's, we had 6 on top, 1 on the bottom. And so the number of x's I ended up with was 6 minus 1. That's +5. So keep those signs straight, because it turns out that after that dust settles, we get one term, one factor, that has a negative exponent, y to the -3, and another which has a positive. And so when it's time for us to clean up the negative exponents, the y's end up dropping from numerator down to denominator, but the x's end up staying in place. And our final answer ends up being x to the 5th upstairs and y to the 3rd downstairs. So x to the 5th over y to the 3rd. Here's an alternative way to deal with those y's using what we were talking about a little earlier. An alternative way to do it, we need to multiply this fraction by y to the -4 on the top and on the bottom. And that would work because now upstairs, the y to the -4 times y to the 4 is going to give me y to the 0, which is going to make those y's go away. And then downstairs in the denominator, we're going to get y to the -4 times y to the 7, and that becomes a multiplication of powers. When you multiply powers, what happens to the exponent? get added together. And negative 4 plus 7 accounts for why we have y to the positive 3 on the bottom. Problems 6 and 7 come to us with a lot more arithmetic going on. In this one, we have a bunch of different factors all multiplied together. We had 2v x to the minus 2, 7v to the minus 1, 4u to the 7, u to the minus 1, x to the minus 4. So a lot of stuff going on. We've got x's, we've got u's, we've got v's, we've got constants, we've got some negative exponents. So we have a lot of moving pieces. And what this person did first is they took a look and tried to get the like factors identified. So we have some powers of x over here, we have some powers of x over there. Commutative property says we can get those next to one another and then use, yet again, the multiplication of powers principle to combine those powers of x together. X to the minus 2 times x to the minus 4 gives me x to the minus 6. Just by adding the exponents, negative 2 plus negative 4. Same thing with the u's. They were already next to one another, and so we didn't have to move them to recognize that multiplying these powers means adding those exponents. 7 plus negative 1 gives me 6. And then the v's. So tell me what's going on with these v's. And they've sort of written it up here, but walk me through it for a second. So first thing we notice is we're multiplying powers of v, and therefore we'll be adding the exponents on those v. But what are the exponents? They're negative 1 and positive 1, respectively. This first v here has an implicit exponent of 1 sitting on it. So when I add those together, 1 plus negative 1 gives me 0. And v to the power 0 means that there are no v's at all. Right? So the v's cancel, as you say. And it's a good opportunity for us to remember that in exponent arithmetic, where we're dealing with the top two layers of the layer cake, when we cancel out a quantity, it doesn't become 0. It becomes 1. Anything to the 0th power, any non-zero quantity raised to the 0th power doesn't become 0. It becomes 1. And so there's a careful recollection, a use, an application of that fact. Any non-zero number raised to the power 0 is equal to 1. And so in effect, what it looks like is it looks like my v's just vanish, because they do. And then we just multiply the coefficients, 2, 7, and 4, multiply together to give me 56. And so after all the exponent gymnastics happen, we end up with 56 times x to the negative 6 times u to the 6th. And then the only final step to do is to transform your negative exponent on this power of x into a positive one, and that was just a matter of moving x to the 6th into the denominator instead. So the final answer on this one, 56 u to the 6th, all divided by x to the 6th. So in our last example, this is the last example that looks an awful lot like our first example from today, because it has a little bit of everything. It's got a power outside of these parentheses with some multiplication and division on the inside. It's got some negative exponents sprinkled in throughout here. So it's got a little bit of everything that we talked about in our first example today. So the first thing this group did is distribute the power of 3 to every one of the factors inside of this giant product and quotient inside the parentheses. And so the coefficient of 2 got the power 3. Don't forget that step. That's another step it's easy to forget. Okay. The x to the power minus 3 got the third power, which, again, power of a power. We multiply the exponents. And so negative 3 times 3 turned into negative 9. U to the 1 to the power 3 ended up u to the third. Z to the minus 2 to the power 3, z to the minus 6. And so that distribution all happened. Simplified the 2 to the third out to 8. Yet another place to screw up. 2 to the third is not 6. It's equal to 8. And then these powers became a part of the numerator multiplying across. And then we got all the x's together. We got the u's. There was only one power of u. We got the z's together. Combine the powers of x by adding, because we're multiplying powers. We're adding exponents. Negative 9 plus 2 is negative 7. Combine the powers of z, and this was a place where I heard from a couple groups, oh, z to the minus 1 on top, z to the minus 6 on the bottom. We have to be a little extra careful when combining those powers. So how did you navigate this step? Because it looks like you went from z to the minus 1, z to the minus 6, to z to the positive 5. So where'd that positive 5 come from? What actually happened at that step? Right. So there, again, we're dividing powers. So since we're dividing powers, we should just be subtracting exponents. That's true whether those exponents are negative, whether they're positive, whether they're zero, whether they're irrational, rational, whether they're crazy, or they can be anything. As long as anytime we divide powers, it's the same as just subtracting their exponents. But when I do problems like this, I have to almost say this out loud in my head so that I don't commit a sign error. That the number of z's that I need is -1 minus -6. And -1 minus -6 is the same as -1 plus +6. And -1 plus +6 is where that +5 came from. So probably the easiest place to make an error on these problems is to screw up a sign on a manipulation like that. And this group navigated it great. There was also, Mike raised an alternative way, the same alternative way that we saw a few minutes ago of approaching this. The alternative way, what was your alternative for this one? You multiplied by how much?
Z to the +6.
Z to the +6. So just multiply it in the denominator by z to the 6th, multiply in the numerator by z to the 6th. In the denominator, it makes the z's become z to the power 0. And so that just turns into 1, again, which explains this 1. And then in the numerator, we get z to the 6th times z to the -1. I'll move that z to the 6th over so that it's next to the z to the -1. And then what do we end up doing with these exponents, -1 and 6? Adding them because we're multiplying those powers. And that again, -1 plus 6 explains why we end up with a 5 upstairs and a 1 on the bottom. So whichever way you slice it, you end up with the same manipulation. So choose the method that you're going to remember. Choose the method that you feel like you have the least opportunity to make a mistake on. Either way you do it, we end up with z to the 5th upstairs and a 1 downstairs. And the only final step that remains is for us to turn this x with a negative exponent into a positive instead, at the cost of moving it into the denominator. And so our final answer is 8u to the 3rd, z to the 5th on top, and in the denominator, x to the power 7.